Hello everyone, Chapter 5, Lesson Alpha, Exponential Functions and their Graphs. Objectives are to review some properties of exponents, graphs, and transformations of exponential functions will then be covered. And then actually we're going to save this for part 2 of Lesson Alpha. We'll save applications of exponential functions for later. I would like to talk about the definition of an exponential function. And actually, I'm going to change something up here real quick. I'm going to call an exponential function the function a times b to the x. And everywhere you see an a here, consider this b. Okay, in my notes as well here. Okay, so an exponential function with base b is denoted by f of x equals a times b to the x, where both a and b will be real numbers, where b is greater than 0 and not equal to 1. Okay, a could be whatever we want it to be, and that'll have effects on the transformation, reflections, all that good stuff. If the absolute value of b, I'm reading right here, is greater than 1, then a growth function is present. If the absolute value of b is less than 1, meaning that the value of b is between 0 and 1, then we have a decay function. Okay, you may remember some of this from higher algebra last year. We're going to get into some specifics next with properties of exponents. Oops. That was my phone. Kids are on their way. I better hurry up. And then we'll get into the specifics of exponential graphs and writing some functions. All right, let's get started. Okay, properties of exponents. These should be review. All of these, and I would review them if I were you, specifically 1 through 7. Number 8 is kind of it rarely is applicable, but it can be in cases. Number 8 rarely comes up though. Okay, so let's take these properties. I'm going to let you review those on your own. And I'm going to use these properties of exponents to write each of the exponential expressions as a single base 2 expression. So right now in number 1, I've got 4 times 2 to the third, which is 4 times 8, which is 32, which is 2 to the 5th. Okay, so this is 4 times 8, which is equal to 32, which is equal to 2 to the 5th. Now there's a bunch of different ways we could do this. Okay, let me do it a slightly different way. Well, 4 is 2 to the 2nd times 2 to the 3rd, which is 2 to the 2 plus 3, which is 2 to the 5th. That's another way we could get to where we want to go. Great thing about exponentials is that there's no one cookie cutter method on how to write it as a base 2 expression. Okay, let's look at number 2. 32, as we just saw, is 2 to the 5th divided by 2 to the 7th. Well, 2 to the 5th divided by 2 to the 7th is 2 to the 5 minus 7, which is equal to 2 to the negative 2. That is a base 2 expression. Another way you could have done that is to take 2 to the 5th over 2 to the 7th, reduce out, so that's 1 over 2 to the 7th, which is the same, they're coming, which is the same as 2 to the negative 7. Okay, properties of exponents, good stuff. Okay, let's write this as a base 2 expression. 16 to the 5th is the same as 2 to the 4th to the 5th times 2 to the 7th. So 2 to the 4th to the 5th is 2 to the 20th. We take 4 times 5 times 2 to the 7th will be equal to 2 to the 20 plus 7, which is 2 to the 27th power. Getting some good practice in here. Hopefully it's going well. Okay, I've got 1 over 2 to the 3rd to the negative x. Okay, so that would be the same as 2 to the negative 3rd to the negative x, which is the same as 2 to the 3x. That's a fun one. Hopefully it made sense. Okay, how about 128 to the x plus 3? Well, 128 is the same as, well, let's think about this. 2 to the 1st is 2, 2 to the 2nd is 4, 2 to the 3rd is 8, 2 to the 4th, 16, 2 to the 5th, 32, 2 to the 6th, just keep multiplying by 2, 64, 2 to the 7th, 128. So I've got 2 to the 7th to the x plus 3. That means I would have 2 to the 7 times the quantity x plus 3, which could be our final answer. Or if we expanded that, we would have 2 to the, that should be a 7, x plus 21. Either of those is very acceptable. Okay, 1 over 128 to the x plus 3. Well, that's going to be equivalent to 1 over 2 to the 7th to the x plus 3, which is equivalent to 2 to the negative 7th times x plus 3, which is very similar to the previous problem. And that would be it. All right, so that's just a rundown of some of our properties of exponents that should be helpful as we go through this chapter. Let's continue. Okay, I want to graph each exponential function and determine the domain and range, as well as find a horizontal asymptote, which an exponential function will have, as well as talk about end behavior. So I'm going to graph 2 to the power of x first. The 3 points I like to use are the points -1, 0, whoops, I want to use a different color, -1, 0, and 1. And the reason why is because I get nice numbers. So 2 to the -1 is equivalent to 1/2. 2 to the 0 is equivalent to 1, and 2 to the 1 is equal to 2. Okay, so I'm going to plot those points, generally speaking. So -1, which would be here, and a positive 1/2, which would be here. And 0, 1, which would be here, and 2, 1, or excuse me, 1, 2, which would be right there. Okay, so this is the graph of 2 to the x. Now you can tell, and just think about if I plugged in a really, really large negative number, 2 to the -100, that'd be the same as 1 over 2 to the 100. That's going to approach 0. So the limit as x approaches -infinity of f of x, or I should write, since I've got a bunch of f of x's here, of 2 to the x will equal 0. The limit on the right-hand side, as x goes to positive infinity, will go to infinity, right? Our graph is rising forever. Okay, so let's see how that would be different than the red function. So if I plug in again the numbers -1, 0, and 1, you'll actually see that the points, they flip positions, right? So 1, 2 now becomes -1, 2, and 0, 1 stays the same, and 1, -1, 1/2 becomes, in this case, 1, 1/2. You can confirm that algebraically. So the graph should look like this. And you might be thinking, well, that looks like a horizontal reflection, and you're actually 100% correct. So the limit in this case, as x approaches -infinity of 2 to the -x, will equal infinity. And the limit on the right-hand side, as x approaches positive infinity of 2 to the -x, will go to 0. All right, let's look at how that's different than the blue function. If I plug in -1, 0, and 1, I'm going to get the same values as the black function, the original, except the opposite sign. Right? So this is going to be, that should be a -1 and a -2. This is going to be a vertical reflection of the original graph, the original parent function. And what you can see with the end behavior is that as we go to the left forever of -2 to the x, we're going to get 0, and to the right, -2 to the x, we will get -infinity. Okay, so each one of those graphs, though, regardless of which one it is, has a horizontal asymptote at y equals 0. Okay, so how would things change if we worked with 3 to the x? Not a whole lot would change. I'd still use the numbers -1, 0, and 1. I would get 1/3, and 1, and 3. Now, you might notice that this point is consistent, and that will always be consistent with functions of the form b to the power of x. Actually, a times b to the power of x for that matter. Okay, provided that a is positive. Okay, so if a is negative, it'll flip that to a 0, -1. Okay, so let's graph 3 to the power of x. So no change with this point 0, 1. However, 1 will output 3 for us. So it stretches it vertically. And then -1 will be 1/3. Limit notation will be the same as 2 to the x for the end behavior, and horizontal asymptote would be at y = 0. Let's continue. Now let's perform a couple of transformations on the parent function that we had before. Okay, so we graphed 3 to the power of x, right? And we said that we had points at each of the following. Okay, the graph looked like this, and there were the points -1, 1/3, and 0, 1, and 1, 3. If I perform a transformation on 3 to the x, in this case, this would be a horizontal shift to the right 2 units. So I'm going to take this point here and move it to the right 2 units, this point here to the right 2 units, and this point here to the right 2 units. And this would be a graph, oops, slightly missed. This would be a graph of y equals, or 3 equals, excuse me, f of x equals 3 to the x minus 2. So the points that I would be translating would be what I had originally, and I'm shifting them. Nothing's changing with the y values, so I'd still get 1/3, 1, and 3. However, I'd be shifting the x values, which was -1. I'm shifting it to the right 2 units. 0, I'm shifting it to the right 2 units. And 1, I'm shifting it to the right 2 units. So here are your new coordinates. Awesome. Okay, so let's take the original function, 3 to the power of x. Let's reflect it horizontally. Okay, which gave us this, I believe. Yep, that's good. So that's 3 to the -x. Now I'm going to shift it down 1 unit. So when I shift that down 1 unit, I get a graph that looks like this. Okay, so when I think about those points, I took -1 and 0 and 1, and I flip-flopped them, right? So I still have those x values that are being inputted, so there's no change there. Okay, the only thing that's going to change is the outputs here. And so 3 to the -x will flip the outputs, and then we're going to shift them down. So we took the outputs, which were 1/3 and 1 and 3. We changed them to 3 and 1 and 1/3, and then we subtracted 1 from them, shifting it downward. So this became a 2 and a 0 and a -2/3. And so there are our coordinates for the 3 points that should be in yellow of that new that function based on the parent function 3 to the power of x. All right, let's keep on moving. Okay, so let's match each of the corresponding functions with their graph. I'm going to analyze the graphs first. It looks like this graph has been shifted up 1 unit. It looks like this graph has been flipped horizontally. Looks like this graph has been shifted down, let's see, 1, 2, 3, 4 units. And it looks like this graph, there's some kind of either compression going on or maybe a shift to the right. Yeah, I think it's a shift to the right. So with that being said, this is a shift up 1 unit. Let's see if I can find something that matches. Yes, I got one. Okay, this looks like a horizontal reflection. Yep, got that one. Okay, this is a shift down. How did I know it was 4 units? Some will make the mistake and think 1, 2, 3 units. Nope, it's 4 units because normally we start here at the point 0, 1. So down 4 units. It looks like I've got a match here. And then by process of elimination, you can see this special point here. That's a shift to the right 2 units. So that would match up there. Okay, let's do a little bit more with transformations and we'll finish up with some equation writing. Okay, determine the parent function and the transformation being performed in the correct order. So the parent function here would be g of x, let's go f of x. F of x is equal to e to the x. So what is going on? It doesn't matter if I list vertical and then horizontal or horizontal then vertical, but within each of those I need to do them in the correct order. So let's go horizontal transformations first. So the first of the horizontal transformations, we have to go outside in. So we're going to say a shift right 1 unit. The second transformation would be the 2, which is a horizontal, be careful here, shrink by a factor of 1/2. And then the third transformation, which is our vertical transformation, is a shift up 5 units. Okay, let's move over to the other. In this case, f of x would be 1/2 to the x. That's our parent function. So let's do horizontal transformations first. So this would be right 9 units. Second horizontal transformation would again be horizontal shrink by a factor of 1/2. Our vertical transformation in this case would be a vertical stretch by a factor of 3. Awesome. Let's write an equation for the parent functions given the following transformations. So f of x is e to the x. We want a horizontal shift right 3 units. We want a horizontal stretch by a factor of 4. You can write this in a couple different ways depending on which one you do first. So if I did a horizontal shift right 3 units and then a horizontal stretch by a factor of 4 and then a vertical shift up 8 units, that would be f of x. We could perform this in a different order. We could go e to the x over 4 minus 3. Okay. Actually, one of these is correct and one of them is wrong. In this case, I believe based on the fact that we have a 1 here and a 2 here, we want them in this order. The correct function for this case would be the second one, because from the outside in for the horizontal, the first thing we would do is a shift, the second thing we would do is a stretch, and then a vertical shift up as well. Okay, now that we've got that down, let's look at f of x in the second example. We want to stretch by a factor of 3, shift up. Okay, so vertically we want to stretch by a factor of 3. We want to do a vertical shift up 7 units, and then a horizontal stretch by a factor of 4. Okay, so we would take 1/5 to the x. We would vertically stretch it by a factor of 3. We would shift it up 7 units, and we would stretch it by a factor of 4. That would be our function for the second one. Okay, let's go ahead and move on to our last slide where we'll look at writing a function based on 2 points. Okay, so here we are. We want to write an exponential equation that contains both of the given points. So we're going to take this function y equals a times b to the x, and we're going to substitute in each point individually. So if y equals 4 when x equals 0, then that means 4 equals a times b to the 0, which I just rewrote. Big deal. Okay, so b to the 0 is equal to 1. Therefore, this is 4 equals a times 1, so a equals 4. So we have the function y equals 4 times b to the x. Now we need to find b, so we're going to utilize the second point to find b. We're going to plug in 16 for y. We're going to plug in 2 for x. We're going to divide both sides by 4. So I get 4 equals b squared. Therefore, since b has to be positive, b must equal 2. Therefore, our function is 4 times 2 to the x. Please don't make this mistake. This is not equal to 8 to the x. That is not at all true. Not at all true, because 4 is not raised to the x power. Okay, let's do the same thing for the second one. So y equals a times b to the x. I plug in a 10 for y and a 0 for x. That means I get 10 equals a. Therefore, y equals 10 times b to the x. I plug in a 6 for y, and I plug in a 3 for x. All right, now I'm going to solve. So I'm going to divide both sides by 10. So 6/10 equals b to the third. I'm going to reduce this. A 2 goes into both of those. Therefore, b is going to equal the cube root of 3 over 5. Or b equals 3/5 to the 1/3. So how would I write an equation for that? Well, if y equals a times b to the x, then that would be 10 times 3/5 to the x over 3. Notice that that is the same as this. Okay, there we have it, guys. That's how you write an equation given 2 points for an exponential function. All right, I hope that made sense for you. Let me know if you got any questions, and we'll see you in the next video.